Hi, it's Mr. Andersen, and this is AP Physics Essentials, video 102. It's on wave amplitude. Amplitude is the maximum displacement of oscillations in a wave. And so let's say we have a tsunami, which is an earthquake underneath the surface of the ocean. If the ocean was totally flat, that would be the dotted line. And so way out in the ocean, you're going to have an amplitude that's really, really low, maybe only 12 inches as far as amplitude go. And that's because they have these really long wavelengths. So you won't see that tsunami coming. As it approaches land, the problem is that the amplitude gets greater and greater and greater as the wavelength gets shorter. And so you can have deadly consequences of a tidal wave or a tsunami as it crashes upon land, but the humans didn't know it was coming. So scientists are working on sensors that can measure the amplitude changes over time way out in the ocean, and they can give us some warning so we can reach safer ground. And so waves transfer energy through oscillations. Those waves could be longitudinal, where the oscillations are in the direction of the movement of the wave, or they can be transverse, where it's perpendicular. But in both of those, the maximum displacement of the wave itself is called its amplitude. And so we could measure that in a longitudinal wave by looking at the density of the compressions in the wave. It's easier in a transverse wave. All you do is look at it at rest, and we measure how high it's going up or how high it's going down. And so if we model that, a transverse amplitude, if we've got a sim bucket simulation here, we've got a rope wave. So the wave is moving from left to right, so the oscillation is perpendicular. But watch what happens as I increase the amplitude. So now we have an amplitude of 1.5 centimeters, and we amplitude it up to 2 centimeters. What's happening? Well, there's more energy in that wave. There's a greater amount of oscillation. How could I, if I'm given a picture like this, measure the amplitude? It's pretty simple. You just measure how high we are above or below equilibrium. So in this case, it would be 2 centimeters. Now, if we're looking at a longitudinal wave, like a sound wave, it's a little bit different. In a longitudinal wave, the oscillations are in the direction that the wave is moving. So the dotted line just represents the direction. But you can see as I increase the amplitude, what's happening? Well, we can see the wave more now. So we're getting more density where that wave peaks out. Now, how could you calculate the wave amplitude if you're just given a picture of a longitudinal wave? It's more difficult, but a good way to do it would be to look at the crest, or the highest point of the wave, and I could count the number of particles inside here. I think I counted it to be around 30. And then I could move to an area, a trough of the wave, and it's going to be around 15. So the density of particles within that area tells me something about the amplitude, and therefore the energy carried within the wave itself. And so did you learn to use graphical representations of mechanical waves to study the amplitude? I hope so, and I hope that was helpful.